Hey guys, and welcome to Unit 6, Trig Identities. So, the first question is, what is a trig identity? And a trig identity is an equation that is always true. Some of the easiest, most basic trig identities are like sine x equals sine x, or cosine x equals cosine x, or tangent x equals tangent x. But then there are a few other trig identities as well. Well, a lot more. The first ones that you can probably recognize is that cosecant theta is equal to 1 over sine theta. Another one is secant theta is equal to 1 over cosine theta. And cotangent theta is equal to 1 over tangent theta. And there's probably a few others that you already know that we're about to go over as well. So let's remember that tangent theta is equal to y over x, and that y is equal to sine theta, and x is equal to cosine theta. Therefore, tangent theta is equal to sine over cosine, and therefore cotangent theta is equal to cosine theta over sine theta, because tangent and cotangent are reciprocals of each other. Boop. Now let's take a look at our even and odd identities. So first, let's just recap that even functions are when we have f of negative x. Then if it's even, then it's going to be f of x. So if we start off with f of x and we make f of negative x and we simplify and we get the same exact thing, we know that it is even. Odd functions are when we substitute in f of negative x, or when we substitute in negative x for x, we get negative f of x. And so these are odd functions. So basically, we have our basic function, whatever that is, and then if we take the negative x of it, does it look like the same function over again, or does it look like the negative of that function? So let's think this through a little bit. The transformation of f of negative x, what does that look like graphically? F of negative x, when we negate the x, we are reflecting over the y-axis. So to think of this graphically, we're going to have to reflect, sorry that I cannot write that fast, over y-axis. And when we reflect the function over the y-axis, it's even when we get the exact same thing. So same as original. Same as original. I can't. Right. All right. Or if we reflect it over the y-axis and we get the negative one, if we get negative f of x, what does that look like in general? It's reflected over the x-axis. Reflect over x-axis. So let's take a look. If we have sine of x, graphing on this is going to be very interesting. If we have sine of x, something like that, right? Looks like that-ish. And then we reflect it over the y-axis. So we're going to reflect it over the y-axis. it's going to look like that for the positive part and this for the negative part. So does it look to be the same exact thing, or does it look to be reflected over the x-axis? Yeah, this is reflected over, the red one is also reflected over the x-axis to the green one. So we would say that sine is an odd function. So sine of negative x is equal to negative sine of x. So let me erase this. So it's equal to negative sine of x because it is odd. Now, let's take a look at cosine. So if we graphed cosine, we start from positive 1 and go down and back up. You know, these are just rough estimations, right? Now, if we reflect this over the y-axis, going down like that, we would also go down like that. And turns out that we would get exactly the same function. So f of negative x would be equal to the same as the original. So cosine negative x is equal to cosine of x. And then for tangent, whoops, boop-a-doop. I have my y-axis, my x-axis, at pi over 2. I have an asymptote at negative pi over 2. And at negative pi over 2 and pi over 2, I have asymptotes. And then, come on, you can work with me. There we go. I want to graph my tangent function. It looks something like that. Now, I'm going to reflect this over the y-axis. When I reflect this part, I get that. And when I reflect this part, I get that. So when I reflect it over the y-axis, does it look to be the same exact thing? Does it look to reflect over the x-axis, or does it look like neither of those two things? Well, if I reflect this over the x-axis, I get that part. And if I reflect this over the x-axis, I get that part. So it turns out that reflecting over the y-axis is exactly the same thing as reflecting over the x-axis. So tangent of negative x would be equal to negative tan of x. So one of the biggest things with this unit, and that's probably the hardest part, is that people tend to complain about that there's just so much memorizing with trig. And it's true, there can be a lot of things to memorize, but the most important part is remembering how to find things out. So one strategy of proving even and odd identities is to graph them out. By this point, we should have a fairly strong foundation in graphing the sine x, cosine x, and tangent x, and reflecting them over the x and y axis. And so after that, you can figure out the even and odd identities pretty quickly. All right, so we've had our reciprocal identities, we had our tangent and cotangent identities, we've had our even and odd identities. Now it's time to get into the Pythagorean identities. All right, so you know this circle, the unit circle. We have, and then this triangle, this right triangle within the unit circle, where the x coordinate or the x value is cosine and the y value is sine, and the hypotenuse is 1. So let's say we wanted to find the side lengths of this triangle. I would say that x squared, using the Pythagorean theorem, x squared plus y squared is equal to hypotenuse squared, 1 squared. So, would you believe me if I said that cosine x squared plus sine x squared equals 1? So all I did was replace x with cosine with x and sine x with y. Well, this is our first Pythagorean identity. This is kind of the base. This is the one that you basically need to remember. Or remember this and then remember that. But for simplicity's sake, I would remember cosine squared plus sine squared equals 1. And you can have x or theta. I should have put theta, but I put x. And then we can also manipulate this. We can subtract sine x on both sides. So, and another thing is that typically we don't write it cosine x parentheses squared. We typically write it as cosine squared x plus sine squared x. Sine squared x equals 1. And then we can do some algebraic manipulation. So I can subtract sine squared x on both sides. And so I would get that cosine squared x is equal to 1 minus sine squared. And that sine squared x, if I subtract cosine x on both sides, is equal to 1 minus cosine squared x. So Pythagorean theorem, cosine squared plus sine squared equals 1, and then these are two variations. So now we're going to find the other, basically 6 Pythagorean identities. So the key here is to start with the Pythagorean identities. So when I learn the Pythagorean identities, I always put sine first. So I'm just, for whatever reasons, I'm so used to putting sine. So I'm going to put sine squared theta plus cosine squared theta. But it really doesn't matter which one you put first. Equals 1. And then I'm going to divide both sides of the equation by sine squared. And by doing this, I am not changing the values of the sides, but I'm using some algebraic manipulation. So if I divide by sine squared theta and divide by sine squared theta, I'm going to have to apply the sine squared theta to both of these. So sine squared over sine squared is 1. And cosine squared over sine squared. Well, what's cosine over sine? Cosine over sine is cotangent, and then cosine squared over sine squared would be cotangent squared. So we would say plus cotangent squared theta equals 1 over sine squared theta. Well, 1 over sine is cosecant, so this would be cosecant squared theta. So 1 plus cotangent squared theta equals cosecant squared theta is another Pythagorean identity. Now, yes, you can totally memorize this, or just memorize the sine squared plus cosine squared equals 1, and then just divide by sine squared theta on both sides, and you'll have this identity. Now, the other two using algebraic manipulation is that 1 equals cosecant squared theta minus cotangent squared theta. That's a 2. Kind of looks like a 3. And then there's also that cotangent squared theta is equal to cosecant squared minus 1. All right. So those are 3 more identities that we can use. The next one, so I'm going to write sine squared theta again. Sine squared plus cosine squared. Now notice that sometimes when I say these phrases, I don't say the theta. It's okay not to say that. You don't have to say it, but you do have to write it. So this time I'm going to divide both sides by cosine squared on both sides. And we're going to get three other identities. So sine squared over cosine squared is going to be tangent squared. So tangent squared theta plus cosine squared over cosine squared is 1. And then 1 over cosine squared is secant squared. So that's one of them, tangent squared theta plus 1 equals secant squared theta. Now, of course, 1 will be equal to secant squared minus tangent squared, because I subtracted tangent squared theta on both sides. And then also tangent squared theta is equal to secant squared minus 1. So this can seem fairly abstract. There's like a point of separation between, working with the triangles or the circles, and now there's just a lot of manipulation going on. And so it can get a little hectic, and you're like where is all of this coming from? So let's just do a quick example of a 3, 4, 5 triangle, and let's prove this one using a 3, 4, 5 triangle. So this is a good strategy if, when in doubt, you can't figure it out, and let's just make sure that it actually works. So we have a 3, 4, 5 triangle. This is the easiest triangle, right triangle by the numbers. So if we're doing tangent squared theta, so if we find tangent is 4/3, and it's going to be squared. Is it equal to secant squared? So secant is the reciprocal of cosine, so 5/3 squared, and then minus 1. So 4/3 squared would be 16/9. Is this equal to 25/9? And then 1, we want to make this 9/9 so that we have a common denominator to do subtraction. And 25 minus 9 is 16, so 16/9. I'm going to try to keep this all in the same one, is equal to 16/9. So it works out that tangent squared theta does equal cosine squared theta minus 1. So this is just a nice way to see visually how it works. All right. So let's take a look at this problem. Cosecant theta over secant theta is equal to cotangent theta. What can we do to start simplifying this problem? Well, we know our reciprocals. Cosecant theta is 1 over sine, so 1 over sine theta. And secant theta is 1 over cosine. And then dividing is like multiplying by the reciprocal. So I'm going to have 1 over sine theta, and it's times cosine theta over 1. And then this is equal to cosine theta over sine theta. And cosine theta over sine theta is equal to cotangent, which is the same. Okay? So this brings us to different strategies on being able to simplify expressions. So the general name of the game is to start by putting everything in terms of sine and cosine. You're going to do this by either changing one side of the equation to look like the other side of the equation, or change and manipulate both sides so that you get them to be the same. All right, so I would like you guys to try to do this one. So pause the video, please. All right, now that we're back, we have secant squared theta times 1 minus cosine squared theta equals tangent squared theta. So we can start trying to figure out a way to get this into in terms of sine and cosine. So secant squared theta is 1 over cosine squared theta. 1 minus cosine squared is equal to sine squared. And if we didn't remember that identity, we know that 1 is equal to sine squared plus cosine squared. And so we would have sine squared plus cosine squared minus cosine squared. The cosine squareds would have canceled each other out, and we would have been left with sine squared theta. And we have equals tangent squared theta. So we have sine squared theta over cosine squared theta, which equals tangent squared theta. So tangent squared theta is equal to tangent squared theta. Boom, boom, boom. Woo! A few other ways strategies for simplifying identities is transforming everything to be in terms of sine and cosine, factoring, multiplying by a conjugate, especially like if you have things in the denominator. Look for Pythagorean identities and variations, and look for common denominators. All right, and then one way to check your work to make sure that these things actually make sense is that you can graph both expressions, either like on a graphing calculator or by making a 3, 4, 5 triangle and see, do those expressions work on a 3, 4, 5 triangle. All right, we're going to do one last one together, just the one on the left, and that's how far we got in class. So cosine x times the quantity tangent x minus secant x. Well, so tangent is sine over cosine, and secant is 1 over cosine. And then we have times cosine x. So if we distribute this through, distribute the cosine x through, we would have cosine x times sine x. Actually, we don't even need to distribute it through. I changed my mind. Let's make life a whole heck of a lot easier on ourselves. So cosine x, since cosine is in the denominator for both of these cancel out, and we're left with sine x minus 1. All right, and so with that, those are our Pythagorean identities, our reciprocal identities, and our even-odd identities as well. And you should be well on your way to finish the first homework assignment. All right, take care. Bye-bye.